Hi, I'm Rob Weston, and today I will be presenting the paper There and Back Again, Learning to Simulate Radar Data for Real-World Applications. This work was carried out by myself, Weavy Parker-Jones and Ingmar Posner at the Applied Artificial Intelligence Lab, University of Oxford. If you have any questions, please feel free to drop me an email or reach out on Twitter. In recent years, there has been a renewed interest in the use of radar for robotics and autonomous driving. In contrast to vision and LiDAR, radar is able to detect objects at far range and under a variety of adverse weather conditions, such as fog, rain or snow, conditions where the traditional sensing suites are very likely to fail. This makes radar a useful alternative. However, radar is notoriously difficult to work with. Here you can see examples of urban radar observations recorded in Oxford. They are characterized by significant noise artifacts arising through complex electromagnetic phenomena combined with an imperfect sensing pipeline. Speckle noise appears as random fluctuations in the radar power field, and ghost reflections arise through complex multipath reflections off walls, for example. More recently, data-driven approaches have been particularly successful at overcoming these challenges across a range of robotic applications. However, the size, labeling, and quality of datasets currently available to the radar community are limited, at least in comparison to those available to the vision and LiDAR communities, and are hindering the continued success of data-driven approaches. Training models and simulation is a valuable alternative. Inspired by similar successes in vision and LiDAR, and in addition to facilitating corner case testing of scenarios which are too dangerous or too expensive to test in the real world, we believe that simulation has an important role to play in training the next generation of radar-based perception systems. The aim of this work is to develop a radar sensor model that is able to faithfully replicate radar sensor measurements in simulation. In particular, we are interested in learning a radar sensor simulator that can be used to train new systems that can be successfully deployed in the real world. Instead of developing a new radar simulator from the ground up, we aim to interface with existing simulation environments. In particular, we consider interfacing with the Kala Autonomous Driving Simulator. As we saw earlier, as a result of noise artifacts, radar observations are inherently stochastic. Two observations viewed at the same location but at different times are very likely to be different. In order to replicate the stochasticity of real radar, we adopt a deep implicit modeling framework. This is achieved using a neural network which takes in a standard normal noise variable alongside the world state. For the same world state, this allows multiple radar observations to be sampled by sampling different values of noise and passing them through the neural network. This allows us to implicitly capture a distribution over radar power returns. We represent the world state as an elevation map. This allows us to easily interface with existing simulation environments without relying on specialized world models. To train our model, we assume that we have real-world radar observations and partial elevation map labels generated automatically from LiDAR. These are taken from the Radar Oxford 10K dataset. This real-world dataset is generated automatically simply by driving around the environment and relying on measurable quantities, without requiring potentially subjective hand labeling. Given the observations we have available to us, the most obvious approach might be to learn a radar sensor model directly regressing from the measured elevation maps to radar observations. Unfortunately, due to the limited range and sparsity of LiDAR measurements, the elevation state can only be measured partially, and we find that models learn in this way poorly generalized simulated world states, as corroborated in the results section. Instead, we adopt a slightly different approach. During training, we generate radar observations directly from simulated state observations. We train our model using an adversarial setup, introducing a discriminator to distinguish between unaligned real-world and simulated radar observations. However, we find that models learn only using this setup learn to generate radar observations that are poorly aligned to real-world states. To further constrain training, we also model the backward mapping in a similar approach to before. The backward model is tasked with predicting the elevation state from real-world radar, and is trained introducing a new discriminator tasked with distinguishing between unaligned predicted and simulated elevation states. By also modelling the backward process, we are able to further constrain training, ensuring that the predicted radar observations remain grounded in the world state. Firstly, we adopt a cycle GAN setup, ensuring that the mapping from radar to state back to radar remains consistent. This is enforced through a cyclical consistency criteria for both the forward and backward processes. Secondly, the predicted elevation state is grounded to real-world state observations where they exist through an L1 alignment loss. Our final training objective is constructed as a combination of each of these loss terms, and both models are optimized together in a joint optimization. The primary motivation for learning a radar sensor model was to assess the feasibility of training models in simulation before real-world deployment. To assess how far we are able to achieve this goal, we consider training a segmentation model in simulation, which partitions the space into occupied, free, and unknown space. The performance of the segmentation model is then evaluated on real-world data using the mean intersection over union metric. As we only have partial labels available, this is evaluated only for the free and occupied space. In order to be successful at this task, the radar sensor model must learn to faithfully reproduce radar's noise artifacts, which the segmentation model must in turn learn to overcome during training. At the same time, the radar sensor observations must remain grounded to the state observation. All labels for this task can be generated automatically using LiDAR measurements, again without relying on having a hand-labeled dataset available. As a benchmark, we compare the performance of each segmentation model trained in simulation to a model trained entirely in the real world, and compare this against several different training configurations. In A and B, the radar sensor model is learnt as proposed earlier by directly regressing to radar observations from partial elevation maps. In A, this is achieved through a simple L1 regression loss, whilst in B, an additional adversarial criterion is added in a similar training setup to PIX. In C, the radar sensor model is learnt simulating radar observations from simulated world states during training, but using only an adversarial loss between simulated and real radar observations. In D, the model is trained using adversarial losses and cyclical consistency in a similar setup to CycleGAN framework. And finally, in E, the model is trained using the full training objective proposed previously. We find that models trained to predict radar observations from real-world elevation maps result in a significant drop in segmentation performance. Models trained in this way fail to generalize simulated world states. On the other hand, models trained on simulated elevation states but using only a GAN loss result in radar observations which are poorly grounded to the world state, again resulting in a significant drop in performance. The best performing model is learnt using simulators trained with a full training objective. Our simulator is inherently stochastic, capturing many of the noise artifacts that characterize real-world radar observations, such as speckle noise, appearing as random fluctuations of power returns, saturation lines appearing as bright radial streaks, and ghost reflections arising as a result of complex multipath reflections. After training, an added benefit we get from adopting the full training criteria is the backward model, which is able to infer the elevation state of the real world. We compare the heights inferred by the backward model with the heights measured in real-world LiDAR for both occupied and free space. And as a benchmark, we compare this to a model trained to directly regress to elevation from partial elevation labels. Using the backward model, we are able to infer the elevation real world to within a 4 to 40 cm accuracy. While slightly less accurate than a model trained to regress to partial height measurements directly, our model is able to better generalize to regions of space that fall outside of the range of LiDAR by learning from full simulated height states generated in simulation as part of our training setup. In conclusion, we consider adopting a stochastic and data-driven approach to radar simulation, interfacing with commonly available simulation environments such as CALA to train new models in simulation that are capable of being deployed in the real world. This is achieved by explicitly training our model to generate realistic radar observations from simulated elevation states, using an adversarial setup. The forward and backward processes are modeled simultaneously to further constrain training through cyclical consistency and real-world alignment with partial elevation labels. As an added benefit, the backward model, learnt as part of the training setup, can be used to infer the elevation state of the world from real radar observations, whilst additionally generalizing to regions of space without training labels. As a potential area for future research, early experiments on a limited amount of hand-labeled training data suggest that the segmentation performance of models trained in simulation drops when considering finer-grained classes. Extending our approach to work in this case constitutes an interesting area of future research, particularly if, when, and as high-quality labeled datasets are released to the community. If you have any other questions, please reach out over Twitter or drop me an email. Thanks for listening.